Okay, so we are now going to start the next section. Having seen in the previous section dual spaces, now we are going to see inner product spaces. So let us recall some things that we already know from our study of physics and geometry. That is, I am talking about vectors, actual vectors. But before we go to that, let us note one thing, that so far, whenever we have considered a vector space V over some field, underlying field of scalars F, the specific nature of F as a field, other than the fact that it is a field, has actually played no significant role. I mean, it was just there in the background, some arbitrary field is there from where we are taking the scalars out and then multiplying vectors with those scalars, and such things we did. But now in this section, we are going to restrict ourselves to these two cases. That is, now in this section, for us, F is going to either be the field of real numbers or the field of complex numbers. So we are no longer going to consider arbitrary vector spaces over, that is vector spaces over arbitrary fields, but our fields will be either this or this. And when the underlying field is this, we call the vector space, whatever it is over that field, a real vector space. And when our underlying field is C, the field of complex numbers, then the vector space is called a complex vector space. Very straightforward names which immediately tell us what the underlying field is. Okay, now we are well familiar with real vector spaces, and in particular two such spaces. One of them is the vector space of two-dimensional vectors, that is vectors in a plane, and the other is, well, we are using actually this notation to denote a vector space, but we can, if we want, we write simply 2. And the other one is the three-dimensional vector space R3, which has vectors in space, all kinds of vectors. Now the question is, under this restricted setup where our F is either R or C, what else do we have in these concrete vector spaces that we have come across in geometry and coordinate geometry and vector analysis? What do these concrete spaces have besides the vector space structure that we can carry over to a more general setting, say an arbitrary vector space over F? One of them is the notion of length. For a real vector, whether in a plane or in space like this marker, there is a notion of the length of such a vector that is there, okay, which we have so far not obtained anywhere for vectors in an arbitrary vector space. And the other notion is perpendicularity, or more generally the notion of angle. That is, we can talk about two vectors being perpendicular to each other, or in general we can talk about the angle between them. And these two notions, as it turns out, are special cases of one thing, and that is the dot product of two vectors. Our usual dot product that we know very well. In fact, we use dot product in physics to calculate the work done by a force. You take the dot product of the force vector and the displacement vector. Say, by applying that force to some object, the object suffers a displacement. So the displacement is also a vector and the force is also a vector. So if you take their dot product, if the force is a constant force, then you take the dot product of the force vector and the displacement vector. Whatever quantity you are getting, that is the work done by the force to move that object or to cause that displacement. Okay, so we know about dot products. Also, dot products help us find components of a vector in some directions. Like, for example, you may recall these things from vector analysis. Say you are given a vector, some v vector, and say you are given another vector, say k. Now the component of the vector v in the direction of the vector k, if you think of it geometrically, it is like this. Say you shine light, say you switch on a flashlight and you shine light, and you look at the shadow of the vector v on the vector k. But in what way are you holding the flashlight? Say, you are holding the flashlight in such a way that the beam is perpendicular to k. Then you will get a shadow of this vector. This shadow is the component of this vector along the direction of k, which actually is the effect that this vector has in this direction. Right. Now to calculate this vector, this shadow, or the projection, you may call it that also, you need dot product, and it is the dot product of v and the unit vector along k, that is divided by the magnitude of k. So you can recall some such things. We already know, we are well familiar with the notion of dot product of vectors. Now, and our dot product that we know of is defined like this, of course, for any two vectors, say v equal to x1, y1, z1 and w equal to x2, y2, z2, their dot product is denoted by this v dot w and is defined to be equal to this scalar x1, x2 plus y1, y2 plus z1, z2 or z1, z2. Now this looks a little weird. It looks like we are talking about coordinates, but of course you can write these vectors in your more familiar notation that you know from vector analysis. In that notation, the vector v, in fact, just to emphasize the fact that it's a vector, we put that arrowhead also over it. It looks like this: x1 I cap plus y1 j cap plus z1 k cap. Similarly, your vector w is x2 I cap plus y2 j cap plus z2 k cap. Where I cap, j cap and k cap are the unit vectors along x, y and z axis, along the positive directions of these axes respectively. These are things we already know. So when we calculate the usual dot product of two such vectors, then we get this scalar. It is not a vector, it's a scalar, and in fact it's a real number. Oh, I must also mention that where these these things x1, y1, z1, these components are all real numbers. So this is a real number. Now I said, or rather what the author is saying is that the notion of length as well as the notion of the angle between two vectors are special cases of this notion of dot product. How? That is like this: the length of the vector v, say this v, is actually, it turns out this is equal to the square root of the dot product of v with itself. And if you look at the formula for the dot product, rather this is the definition of dot product itself, then you get this: x1 square plus y1 square plus z1 square, which is indeed the length of this vector or this vector, same thing. And when two such vectors are given v and w, then the angle between them is given by this formula, this next one that now I'm going to write. If theta is the angle between them, then cos theta is v dot w divided by the square root of the dot product of v with itself times this square root of the dot product of w with itself. And this also you know why. So because if you write this thing in your more familiar vector analysis notation, then this is v dot w, and this is the length of v, and that is the length of w. So if you rearrange things a little bit, you get this. Which is in fact how dot product is usually defined in vector analysis. And then later on, when vectors are expressed using their Cartesian components, then it turns out that the dot product ultimately is given by this formula. You can use this one to get this or this one to get that, and you get the same thing. Okay, so this is how from the notion of dot product itself, the notion of length and that of the angle between two vectors come. These two notions come from the notion of dot products. So that's why they are special cases. Now the question is, can we extend this to the case where in place of R we have C, the field of complex numbers? We can just simply blindly extend this definition, but that will give us problems. What sorts of problems? To understand what goes wrong if we just simply blindly extend this to the complex case, let us write down some elementary properties of dot products. That is, this dot product that we already know in our space R3, that is 3D space. These properties are well known and very natural. The first one of them is this. If we have said such vectors, then the dot product of V with itself is a non-negative real number, and the dot product becomes the zero scalar, that is the real number 0, if and only if V is equal to 0, that is if and only if V is the 0 vector. And these properties are things that we already know or can be verified quite trivially, directly, without any twist. And then we also have another one which says that the dot product is commutative. The order of the vectors of which you are calculating the dot product does not matter. Okay, you can take any order. And the third one, there is a third one also, which is a sort of distributive law. It says that dot product distributes itself over vector addition, like this. Say you take another vector u, then u dot, we throw in scalars also in order to make it somewhat more general. Alpha v plus beta w is equal to alpha times, oh this is not v, this is u dot v plus beta times u dot w. Dot product distributes itself over vector addition. And these three properties are of course true for any real vectors u, v and w, and real numbers alpha and beta. And any real numbers alpha and beta. Okay, now the extension that I was talking about just now, that we want to extend the notion of dot product to the case where, say, the vectors have complex number components. Okay, that is not unnatural for us, because we have already seen vectors over arbitrary fields. So why not over complex numbers? And because we are allowed to consider that case, real case we already know from our geometry and vector analysis, but complex case. So whatever extension we want to have of the dot product to the complex case, we want to not lose these properties as much as possible. So what goes wrong if we just simply blindly use the same formula to define the dot product in the complex case that we have in the real case? So now your vectors are these. Again, this and W but now the components are general complex numbers. And say by defining the, similarly the dot product and blindly, I mean this. Just you simply define v dot w to still be this scalar x1 x2 plus y1 y2 plus z1 z2 or z1 z2. Okay, so now you recall that in the real case our v dot v was used to define the length of v. In fact, the length of v, it turns out, is equal to the square root of this. But to make things meaningful, geometrically meaningful, here also we would want the length to be something that is like an actual length, that is a non-negative real number. But the problem is that if this is our definition, then that may not be the case. And in fact, we may end up having, you look at this property has a name. It is called, you can at least express it like this, that the length of every vector is a non-negative real number, and the length is 0 if and only if the vector is 0. We do not want to have a definition of length which gives us 0 length for a non-zero vector, because that does not make sense. However, if this is our definition, then we have such examples. Say our v is this 1 comma I comma 0. Let us try to calculate v dot v in this case using this formula. It will be 1 times 1 plus I times I plus 0 times 0. So 1 plus I square gives us 0, so that means we are getting 0. So we are getting the dot product as 0, whereas the v itself is not 0, because in order for it to be 0, all the components should be 0. So this problem is there, and in fact you can pretty much understand that this length, in this case it has become 0, but you can of course consider some other v for which the length need not even be a real number. Forget about being non-negative, it may not even be a real number, it may be a non-real complex number. You can very easily find one such example. Say you take v equal to, what can I take? Say, let me tweak this one itself, 2 comma I comma 0. Then for this v, what is our v dot v? It is 2 square. Oh, we are still getting I square, no? So let me change the components a little more. Say I take 1 plus I 0 and 0. For this value of V, what is my V dot V? It is 1 plus I whole square plus 0 square plus 0 square. 1 plus I whole square is 1 square plus 2I plus I square, and 0 square of course we need not write. 1 and I square, they cancel out and we are left with 2I. And it does not make sense to say that 2I is greater than or equal to 0. In the field of complex numbers, we do not have such ordered relations that will allow you to say that this complex number is greater than that. We do not have such things. So that's why this definition is not giving us the things that we want. We want to have these things. So we need to change this definition slightly, and the required change will be this. Instead of defining the dot product like this, our new definition now is this: x1 x2 bar plus y1 y2 bar plus z1 z2 bar, where bars of course denote complex conjugate, because do not forget that these x's, y's and z's, they are complex numbers, general complex numbers, so we can calculate their complex conjugates. Okay. Now do we get this, say, property 1? What do I get? And now if I calculate V dot V, say, then I get x1 x1 bar plus x2 x2 bar plus, no, what am I writing? It's not x2. It is y1, okay, there is not 2. x1, y1, y1 bar and z1, z1 bar. So from properties of complex numbers, this becomes the square of the absolute value of x1 plus this plus this. Now x1, y1, z1, these are general complex numbers, fine, but this square that you see here is a non-negative real number, because that's what it is from, again, properties of such things. So this is a non-negative real number, this is a non-negative real number, this is a non-negative real number, so their sum is a non-negative real number. And if my V is 0, that means all these complex numbers are 0, then of course this quantity is 0. Conversely, if this quantity is 0, then each term should individually be 0. That is because there is no having negative terms and having cancellations of things, so those things are not possible because we are having non-negative term. So if each component is 0, then these individual terms in this sum, they are 0. So that proves that no, okay, I messed up a little. If this sum itself is 0, that is if the dot product is 0, then individual terms are 0 and hence the components are 0, and that is why the vector is 0. So yes, for this new definition, my property 1 is still intact. However, we do lose property 2. We do not lose property 2, but it has to be modified slightly this way. Instead of having 2, now we will have this. That is, on the right side we have to just put one complex conjugate. And when our things are real, of course this becomes equal to this. So that means, that's why I was saying we do not actually lose property 2 if our underlying field is in fact the field of real numbers, and we keep on saying, say we keep this one, then this reduces to this. So that means we can say that in a sense we have also obtained 2, although not in this form but a slightly more general form, a new 2. What else? This 3 itself is, this also has to be modified slightly. However, we obtain something else. That is, something else like this is still true. That looks like this. Alpha u plus beta v dot w is alpha times u dot w plus beta times v dot w. And there is a fourth one which looks like this, but there is a slight modification. And the fourth one is this: u dot alpha v plus beta w is, now we no longer will have simply alpha here, but rather its complex conjugate times u dot v plus the complex conjugate of beta times u dot w. I haven't again written 1 because just like how we had 1 in the real case, in the complex case nothing changes. 2 however changes form, so I have written 2. In place of 3 we do have 4 here, but in a slightly modified form. And the other one, which is this one, there we do not need any complex conjugate or anything. It just simply is true like this. Okay. So we can, just like the real case, we can write for any complex vectors u, v and w, and any complex scalars or complex numbers alpha and beta. Right, so these are concrete specific functions, or these are nothing general or anything like that. Keep in mind that the vector spaces where these dot products have been defined are concrete fixed cases. The first one is the real vector space R3, and this complex one is the complex vector space C3. Okay, so in R3 we already know what dot product is from physics and geometry. In C3 we have first of all tried to extend this, that just following the similar definition, which fails us. We do not get what we want, but then we do this slight modification and we somewhat salvage matters. We get the first one we get as it is, the second one has to be modified slightly, and we get a third one, and the fourth one, which is like this third one, has to be modified slightly. Okay. Now can we, using these things as experience, define something similar in a general vector space, but where the field is either the field of real numbers or the field of complex numbers? When we try to do that, we get the notion of an inner product space. So that is the definition from where this thing starts, this section actually starts. So now we are going to write the definition down, and then we will see what it means and what its consequences are. Let V be a vector space over F. Suppose that for any two vectors u and v in V, there is defined a scalar which we denote by this symbol in F, such that the following properties are true, and we take our cue from those properties that we have seen just now. Number one, u comma u is a non-negative real number, and this is equal to 0 if and only if u is equal to 0. Number 2, the vector the scalar u comma v is equal to the complex conjugate of the scalar v comma u, which mimics this property. And number 3, unlike 4 of them, we are going to have 3 of them, just like how we have them in the real case. U comma, well, is it this one or no, it is this one. Okay, it is this one. This one comes afterwards. Alpha u plus beta v comma w. Do not mess up the notation. Okay, we are not writing any dot or anything here. Alpha u comma w plus beta v comma w. for all u, v and w in V and alpha and beta in F, then V is called an inner product space. Actually, there are quite a few things that need to be understood about this definition. So now we are going to take them up one by one and decipher them. So let us see, but before that I think I need a little ink. I forgot to refill before starting the video. But anyway, we won't need much, only a little bit. So what the definition says is that V is a vector space over F. If you follow the text, before the definition, the author actually repeats that do not forget that for us F is not any F, but F is either R or C, because otherwise these conditions will be meaningless. Okay, so with that convention that F is either R or C, we then further go on to write these things. Suppose that for any two vectors u and v in V, keep one more thing in mind, that V may be a general set, but F is either the field of real numbers or the field of complex numbers. V actually can have many different types of things. Say V may have actual vectors, or V may have functions in it, or matrices in it. So those things are possible. You already know that in a vector space the vectors can be many different types of objects. Okay, so for two such objects, two such vectors u and v, say there is defined a scalar in F. That means this is either a real number or a complex number. In general, it's a complex number, such that this complex number is actually a real number, and that is also non-negative, and it is equal to 0 if and only if our vector u is the 0 vector in our vector space V. Number 2, the complex numbers u comma v and v comma u are related to each other like this. And number 3 is this. Here also there are some things to note. Note that okay, so this statement is about three vectors u, v and w and two complex numbers alpha and beta. So by definition this left hand side is a complex number, and it makes sense to consider this here and w here, because alpha u plus beta v, this linear combination, is an element in V, and w of course is again an element in V. So we can consider there. We haven't said anything about what this thing is, but we can consider their pair like this, which is a complex number. Now this third one says that it will be equal to alpha times u comma w plus beta times v comma w. Note that this is a complex number, alpha is a complex number, this is a complex number, beta is a complex number. So the right hand side is also a complex number. The right hand complex number is equal to the left hand complex number. So it makes sense to have this equation, and that is why here the plus you see is the plus in the vector space V. It is vector addition, but this plus that you see on the right side of the equation, that is your ordinary addition of complex numbers. Okay, if these things are true, then V is called an inner product space. But Keep in mind here we are not just simply talking about the vector space V, but the vector space V along with this function, which will itself be called an inner product on the space that is there, which is defined on the space. Now let us look at what type of function are we looking at here. It's a function whose structure is like this. That is, I can denote the function like this. This is how an output looks, and we have two places for our input. So the domain of the function is the Cartesian product of V with itself, because we are going to consider an ordered pair of two vectors, and we have just simply decided to use that same notation as our output, and our output is a scalar, and such a function which satisfies these three properties is called an inner product on V. This notation may look a little strange because something else is used more frequently in place of this notation, and then something else is this. Instead of using round brackets, people use angular brackets to denote the inner product of two vectors. That is also there. If you are using this notation, which Herstein is not following, then your inner product function will look like this. The function is still same, its structure is still same. It has V Cartesian product V as its domain and F as its range or codomain, whatever you want to call it. Also, do not forget that not every function that looks like this is an inner product. Besides being a function like this, it needs to satisfy these three properties, then only it will be an inner product on V. Right. Now let us look at some of the, now let's look at these things and the consequences, the immediate consequences that these properties have. Okay. So what we said is that the inner product of two vectors is a complex number. Even when this F is the field of real numbers, we can call real numbers complex numbers, because real numbers after all are complex numbers, where the imaginary parts are 0. So in general, these things are complex numbers. Fine. So now, if I take, say, this inner product value, then I can apply property 2 to it. Say, in property 2, you take V equal to U. You can take any U and any V, right? So then property 2 is true. That means we should have this for any vector U in our vector space. But what does this tell us? It tells us that the complex number U comma U is equal to its own complex conjugate, and that happens only when a complex number is actually a real number. And that is why this is in fact a real number. And so it makes sense to say that that real number is non-negative. So although we start with property 1, but it in fact is a consequence of property 2 that this u comma u is already a real number. Now what extra is property 1 saying about u comma u? Namely that it's a non-negative real number, and further it is equal to 0 only in the case when u is equal to 0. Okay. And now let us go back to that property 3 that we wrote there about that dot product that we extended to the complex case. That is, if we have, say, in our general setup here, if we have all these things, say alpha, beta, u, v, w, then what will this be? U comma alpha v plus beta w. Let us try to calculate this using only these properties, because that's all we have. We don't really know what v is, what the set v is, or in fact what the actual inner product function is. It may be anything, any function satisfying these properties. So then all we can do here is that we can interchange the vectors, but when we do that we have to follow property 2. So that means in place of this, if we write alpha v plus beta w comma u, then we cannot just simply write this, but we have to put that bar. Okay. Now here inside the complex conjugate bar, under that we can use property 3. So if we use that, then we are going to get what? Alpha times v comma u plus beta times w comma u, and the bar of course is there. Now from elementary properties of complex conjugates, when you have bar, it distributes itself over complex addition as well as complex multiplication. So that means this thing is equal to alpha bar v comma u bar plus beta bar w comma u bar. Now alpha bar stays like alpha bar, but here we can again use this thing, property 2, and write it as simply u comma v. Similarly, this one also is u comma w. Now if you go back to that property 3 for complex inner product that we defined and then wrote its properties down back then, there you will see that we have in fact written this thing. So that means whatever we have there in the complex case, that is in this space, is also in general true, and we need not consider it as a separate axiom in the definition of an inner product space, but it now becomes a consequence of the definition itself. This is nice. So that means our definition has some meaning, right? Now before further things are defined, in the text the author provides some examples of inner product spaces. So now we are going to go through 3 examples, and the first one of them is rather quite straightforward. Example 4, 4, 1. And again we may quickly forget the fact that f is actually either r or c, so I will repeat it quite a few times. Now the author has said that f is either r or c, and then after that he does not bother again telling us, again reminding us. So he just simply writes, in the vector space Fn, we already know what this space is. It is the space of n tuples of field elements. We have seen this for in general f, but now our f of course is a special kind of f. Define for two vectors u equal to this n tuple and v equal to this n tuple. The inner product of u and v by this formula plus alpha 2 beta 2 and such terms are there, and eventually we have alpha n beta n. Okay, now say you want to prove that this is an inner product, then what do you have to do? First of all, definitely this is again a function that it has the structure of an inner product, that is such a function, because it takes two vector inputs and it gives out one output. Oh, okay. I think I made a mistake in writing this, because this f is not specifically given to be the field of real numbers. So let me just, here I have not written the bars, but I am pretty sure, almost 100% sure, that in the text we have bar. Anyway, so suppose that I am true and this is what we have in the text. So let us now try to verify that this is an inner product. First of all, the function has the form of an inner product function. It takes two vectors as input and it gives out a complex number as output, because these alphas and betas, these components are in general complex numbers. Fine. So then we have to just simply verify those three properties. Let's first verify property 1. What is u comma u? According to this formula, it is this So just like that previous complex case, we will have this sum of squares, which definitely, no matter what the complex numbers alpha I are, is a non-negative real number. Also, clearly, this sum is equal to 0 if and only if each one of these complex numbers is equal to 0. That is, our inner product is the complex number 0 if and, let me write in short like this, IWF if and only if u is equal to 0. The 0 tuple, all of whose 0 n tuple, all of whose components are the equal to the complex number 0. So that means property 1 is true. What about property 2? U comma v comma u bar, say. So this will be v comma u we are writing, okay. So that means beta 1 alpha 1 bar, and like that it goes beta n alpha n bar, and on top of all this we have a bar. So using the fact that bar distributes over addition as well as multiplication of complex numbers, we have this alpha 1 bar which you can see if you take the complex conjugate of the complex conjugate of a complex number, you get the original complex number back. This is one of the properties of conjugates. So you just simply get this, which is nothing but u comma v. So that means property 2 is also true. Then property 3. For property 3 we have alpha, we would need another one. No? Let W be this interval gammas, then alpha u plus beta v comma w. This will be equal to alpha 1 plus beta 1 times w bar. No, sorry, it's not w bar. I need to pay attention more. Gamma 1 bar plus so on alpha n plus beta n times gamma n bar. When we work with this kind of symbols, no, we may get confused very easily. So it's always good to first of all go through the calculation and then check once to see if everything is alright. Now these are just simply complex numbers, so we can write things like this: alpha 1 gamma 1 bar, doing whatever needs to be done and collecting everything. Ultimately we get this alpha n gamma n bar plus like that. If we take beta as common out, then beta 1 gamma 1 bar plus beta n gamma n bar, and you can see that this is nothing but alpha times u comma w plus beta times v comma w. So that means property 3 is also true. So this is an inner product on Fn. Then we have the second example. The second example is a little not so straightforward. Straightforward. In F2, here we do not have arbitrarily many components, but only 2 components. for u equal to alpha 1 comma alpha 2 and v equal to beta 1 comma beta 2, the inner product u comma v to be this complex number 2 alpha 1 beta 1 bar plus alpha 1 beta 2 bar plus alpha 2 beta 1 bar plus alpha 2 beta 2 bar. Again, this function also has the form of an inner product in this vector space, but you have to of course verify the three properties. Out of those three properties, I will verify only one, and the second one and third one they will be left to you because they are quite straightforward. The first one goes like this, just like our how that one went. So what we first do, we first calculate u comma u. So now we do not have any betas, only alphas. So the first term here is this alpha 1 bar, then alpha 1 alpha 2 bar plus alpha 2. Keep in mind that although we have alphas, but 1 and 2 are still there. Alpha 2 alpha 1 bar plus alpha 2 bar. We need to show that this is a non-negative real number. The first term will give us no problem because it is itself a non-negative real number. It's the square of the absolute value of alpha 1. The last term also, let me write that one after this, is also one such term. But what about this one? Alpha 1 alpha 2 bar plus alpha 2 alpha 1 bar. If you look carefully, this is alpha 1 alpha 2 bar plus alpha 1 alpha 2 bar. Because when you distribute this bar over this product, you will get what? Alpha 1 bar and alpha 2 bar. That means alpha 1 bar alpha 2. So alpha 1 bar alpha 2. So that means it's the sum of a complex number and its complex conjugate. And this thing we know, we already know that this thing is equal to, so I need to write the whole thing again. This thing is what? When you consider this somewhere z is a complex number, then it gives you 2 times the real part of z. You recall these properties. So 2 times the real part of alpha 1 alpha 2 bar. Right, so fine, it seems like it's okay, we are getting a real number because this is real, this is real, this is also real. But there is a problem. The problem is that we do not just simply need a real number, but we need a non-negative real number. So that means, although this calculation looks promising, but it will not give us fully what we want. We need to change it a little bit. So let us try once more in a slightly different way. So again we write u comma u, but we now already know a little about what it's going to be. So what we are going to get here is this: alpha 1 bar plus alpha 1. So the trick that we are going to apply here is to write this as 2 alpha 1 bars and put this one with the other things, plus alpha 2 bar plus alpha 1 bar plus alpha 2 bar. Now the first term, just like before, is just this, and if we look carefully, is it this product is this part inside the round brackets equal to this product? Let us see. Alpha 1 bar alpha 1 bar plus alpha 1 alpha 2 bar that we have here plus alpha 2 alpha 1 bar plus alpha 2 bar, yes, and this is nothing but the complex conjugate of alpha 1 plus alpha 2, and this is again a product like this or like this. So this is the square of the absolute value of alpha 1 plus alpha 2. Now this is a non-negative real number. So now we can write greater than or equal to 0. And if u equal to 0, that is both, because u is alpha 1 comma alpha 2, both alpha 1 and alpha 2 are 0, then of course this is 0. We can just simply see that from here, from the definition itself. But what about the converse? The converse is where the actual thing is there. I mean, where you may have to do a little, put some effort. Then, of course, this is the complex number 0. Conversely, if the inner product is 0, then this is 0. We will not use this one because this has not given us anything. I mean, it has given us what we want, but not fully, and we are not happy with that. We are going to use this one. Then this must be equal to 0 because that's what the inner product has turned out to be. But what does it mean? It means that this is equal to 0 and this is also equal to 0. Now this being 0 means what? The complex number alpha 1 itself is 0. But if alpha 1 is 0, then you put alpha 1 equal to 0 here, you get the equation reduces to the square of the absolute value of alpha 2 is also equal to 0, but then that in turn implies that alpha 2 is 0. And they are 0, so u is 0 because u has them as its components. So that means we have proved that u is 0 if and only if u comma u is 0. So this completes the verification of part 1 for this function. Part 2 and part 3 are left to you, and they are straightforward. We do not have any such twists in part 2 and 3. And you will see that it becomes an inner product. And finally, we are going to see another example. This is the third one. And this one is a little analytic. It comes from analysis or calculus. Let V be the set of all continuous Now, before I continue, let me draw your attention to one thing that we have seen today. While dealing with something in mathematics, not just me or you, almost everyone struggles. It's not that some genius just sits down to practice mathematics and whatever that person is presented to, it will fall immediately in place. That is not the case. Everyone struggles, and so here I won't say we struggled, but we just saw that this is a dead end. So the thing that I want to say here is that you may actually do a calculation which is correct mathematically, but it may be useless. Okay, it may not give you what you want to achieve in that situation. So keep that in mind. Let V be the set of all continuous complex valued functions on the closed unit interval 0, 1. And if we take this set of course is a vector space where addition and multiplication by complex numbers are defined point-wise. I think you will understand what that means. But anyway, we are going to see what that means. Let me complete writing this. If f of t and g of t are two such functions in V, then we define an inner product type of function for them which is this integral dt. Now say you want to first of all so here the job is again to prove that this is an inner product on this vector space. But let us first see what the vector space is. Now, what will it mean to add two such functions? That is rather easy. Their sum will again be a function whose domain is this into the field of complex numbers, because keep in mind this type of functions only we are considering in V, and that too not just any this type of function but continuous functions. And it is defined like this by this formula. It is defined to be just the sum of the f and g values at the input t. So that is our addition in this vector space. And for scalar multiplication, if you consider one complex number c, then what does it mean to multiply the vector f by the scalar c? It is also, we need it to again be an element in V, so we also need it to be such a function, and its definition is just this: evaluating this function at t means it is defined to be just the product of the complex number c and the complex number f of t. It turns out that under these two operations, with this one as vector addition and this one as multiplication by scalar, this is a vector space. And in actually verifying this fact, we need properties of such continuous functions that we already know from calculus, or well, not exactly calculus but from elementary complex analysis. You see, do you recall that any such function, here the input is a real number but the output is a complex number. So any such function has two parts, just like any complex number has a real and imaginary part. Any such complex valued function has a real and imaginary part, and both of them are functions. Say you call it, say, f1 of t plus I times f2 of t, where f1 and f2 are both functions again having the closed unit interval as their domain, and into the field of real numbers this time. These are real valued functions, and this is continuous if and only if these are both continuous. Continuous real valued functions like this, that look like this. That's a fact from elementary complex analysis, or it is something that you can just simply prove very quickly and easily. And if you are a little confused about the meaning of continuity, then the meaning of continuity is just that meaning that you have from analysis. Say let me just say that also. Say you are saying that this f is a continuous function from 0, 1 to c. What does that mean? It means several things, but the first thing that comes just from the definition of continuity is this: f is continuous at every t naught belonging to 0, 1, and that itself means that this limit exists and is equal to f of t naught, where you already know what the limit itself means. It has this that epsilon delta definition. The only thing you have to keep in mind here is that when your t naught is 0, then this limit is a right hand limit. There, in that case, there is no left hand limit, and when your t naught is 1, this limit is only a left hand limit. Let's say. Now, when you try to verify that this thing is an inner product, first of all, you have to make sure that this function is well defined. That thing is still there. No matter what function you define in any part of mathematics, it needs to actually be a function. It needs to be well defined. Okay. So, what does that involve? Note that the definition involves an integral. Now, what does this integral itself mean? It has its own meaning, and that meaning also comes from complex analysis. This, for example, this integral is defined to be equal to this integral plus I times this integral. Now the thing here is that if f of t and g of t are both coming from V, our vector space, so both are continuous functions, then their real and imaginary parts are also continuous, and from that you can prove that the complex conjugate of g is also a continuous function, and hence the product of these two continuous functions is continuous, which is a property of continuous functions. So that means this is a continuous function, so its real and imaginary parts are also going to be continuous real valued functions, and we know that such functions have Riemann integrals. So that's why these integrals exist for this integrand, and they are your normal Riemann integral that you know from real analysis, and they are real numbers, unique real numbers that will come for this f and g. So that means this is a unique complex number, and that is why this function, as a function, it's actually a function, it is well defined. And then you have to verify all those three properties that I am leaving to you. But again, in verifying those properties, you have to use elementary properties of such integrals. But again, if you just simply look at property 1, what is it that you have to prove? You have to prove that this is a non-negative real number. What is it? It is this. Now the integrand itself is a non-negative real number. So from this you have to somehow figure out, using properties of integrals and using this definition of integration and using the fact that these are Riemann integrals, that this is also going to be greater than or equal to 0. And in fact it is 0 if and only if the function f is identically 0, that is, at every point in this closed interval it gives the 0 complex number as value constantly. The other properties are easier than this, and they follow the fact that integral is linear in nature, they're like differentiation. And so this verification is left to you, just like part 2 and 3 of the previous example. I won't say anything further on this. And with that, I end the video itself. In fact, this vector space turns out to also be a ring of continuous functions whose ideals, specifically maximal ideals, have some nice structure. But anyway, so let's just keep things till this itself, and the next upload is this coming Friday, and on Friday let us again do calculus. So with that, so that will be all for tonight. So see you on Friday with calculus. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.